Hello. So, today's agenda is to compute the weighted shortest path tree in a graph in which the edges are weighted. So, let me begin with a small example. Consider a graph Now, our intention is to use the same breadth first search technique on this graph and see what happens. So, suppose I start with S. So, in the beginning I have in the Q, this is my Q, I put S inside this, and then when I take out, I visit A and D and set their states to be current. So, this Q takes S out and then it puts A and D. The D value of A is 4 and that of D is 10. So, let me just write down 4 and 10, and then you take A out. So, let us take A out. And you are going to place B and C. So, let us put B and C. So, the corresponding values will be 18 plus 4 is 22. And 24. Okay. And then we take D. So, D is taken off. Once D is taken off, we see that C is again a neighbor. At that time, you notice that the potential D value of this would have been 10 plus 10, which means 20. Okay. The D value of C has already been set as 24. So, in the breadth first search algorithm that we have discussed in the last lecture, what would have happened is that we would have ignored that value, a new value of C, but that would have been wrong. What we have found is that in the second visit to C, we have found a better or shorter or less weighted path to C. So, it is no longer possible to ignore that. In other words, in each case we find a new value for C which is better, we will have to update it. So, this should be changed and made 20. So, in our algorithm we will have to make provision for this change. There is another thing that is happening. In the previous version of the algorithm, the value, the D values were monotonically non-decreasing, which means that the vertex later on or vertex further away from the head had greater than or equal to D value than the vertex which was closer to the head. But now you notice that opposite is happening. So, we can no longer work with this kind of a Q data structure. So, now onwards we will have to change this to something called a priority queue. This is a data structure in which we in normal sense insert a new element, but every time when we extract an element, we extract the element with the least d value. Okay, so let us do these changes in the algorithm. So, here I have the old algorithm as it was stated in the last lecture. It is exactly the same. But now I am going to say that this is a priority queue. And now if you notice here, we extract the vertex with the least d value from the queue and visit all its neighbors, There are three possibilities. There are three kinds of status values. Either the current status value is unvisited for that vertex, or that neighbor v, or it is current, or it is possible that it is status complete, visit complete status. So, what we did was, when it was unvisited, we were normally processing, we were just setting the value to be current, we are setting the d value to be d value of u plus the weight of the edge v uv. Earlier it was 1, now it is whatever the corresponding weight is. And then we were setting the parent of v to be u, and then we put that vertex into the queue. But now, as we noticed in the example, we can not ignore any other situations. We will do the following. What we will say is, else if the status of v is current, then this is a situation when the v is in current status. That means it is already in the queue. It has a d value assigned which is other than infinity. Of course, d value is assigned infinity earlier. So, in this case we will just update the d value. So, we will set d of v as the, what is the value that we set? We will set the d value to be the smaller of the current value and the value that we would have gotten through u. So, we will set to the min of du plus w uv, and the other possible value is the old d value. So, we will just set it to be there. So, possibly if we have improved the value, then we will pick this value, otherwise we will stay with the old value. Now, in case we have changed the value, so if dv is changed, then we need to do a few bookkeeping steps. We will have to set the parent of v to be the new vertex u, because now we have found a better value through u while approaching through u. Sorry, the d value, the parent of v value. So, the parent of v is u. We do not have to change the status, it is staying current, We do not have to enqueue the structure Q, vertex V into structure Q, but we will have to update the Q, because one of the vertices which was presently in Q, its value d value has changed. So, certain internal changes has to be done. So, we will just say update Q. So, we have added this piece to accommodate a better value of dV. What happens when the status of V is visit complete? We do nothing in this case, and then we just normally complete the thing. Vertex U, which was being expanded in this iteration, gets into visit complete status, and we return this structure. Well, it seems it should work, but of course, we have to prove the correctness. So, now we are going to prove that indeed this computes the desired weighted shortest path tree with respect to vertex S. All right. So, let us start with this simple observation here. Let us notice that all the vertices at any given time, at any iteration I, the set of vertices which are in state visit complete are, say, denoted by these dots inside this. Now, what we notice is that all the vertices in state current must be adjacent to some vertex inside this, because only these vertices were expanded and all their neighbors were visited. So, any vertex which is in current state can have edges like this. So, I may have edges like this, or I may have edges like this. So, let us put another boundary and think that all the, so this is visit complete, and these are current, and outside this are unvisited vertices. Okay. So, I will just call these unvisited, okay. Maybe I can just draw a solid line. So, there are these three sets of vertices. So, all the V is partitioned into these three sets. Edges from here can run within it or can go here, but no edge can go from here to here, because if there were one, then we would have, while expanding this, I would have visited that vertex, I would have set its status to be current, I would have set its d value to be anything, computed through this, and so on. So, this is the situation. We will keep this in mind. Now, first thing I want to do is to define a few notations. Okay. So, let us just denote by del w x comma y as the weight of the minimum weight path from x to y. Note that in case of directed graphs, it makes sense to specify this. In case of undirected graph, x to y and y to x would be same. Let us denote by Si the set of vertices in visit complete state at the end of ith iteration. That is this set of vertices at the end of the ith iteration. I will denote them by Si. I will denote by P subscript Si as the set of all paths. This is the set of all paths starting at S and having all intermediate and having all intermediate vertices in Si. So, let us take a situation. So, if I happen to have, so S is of course here right from the first iteration. So, there is a path which looks like this. Which starts at S, ends at X, and all vertices except the last one, which means the first vertex is S, the intermediate vertices are these and this. They are all inside Si, which means all but the last vertex must be from Si. Okay, this is Si. Assuming that this is the picture after ith iteration. So, such paths are member of this set. Del W Si Sx. Now, if I consider all such paths from which are from S end up in X, X could be here or could be here, you can't go here of course, and all the vertices except the last one are inside Si. Among all the paths which end up in X, what is the shortest path? What is the path with minimum weight? That is this weight. So, the weight of all paths in PSI, that weight of the weight of the minimum weight path in PSI that end in X. Okay. So, if you happen to have more than one such paths, then pick the lowest weight, and that weight is denoted by this. And one more thing I am going to denote is d I x is the d value of x after ith iteration. There is one more point, that in case there is no path in PSI which ends in x, then this value will be infinity. Now, let us make few claims. Claim 1. Once again, if you look at the algorithm, what you notice is, once we pick a vertex u from the Q, we expand it, we visit all its neighbors, we update their d values if necessary, or set the new values. Once that happens, you are setting its status to visit complete. And once that is done, notice that it is never entered into the queue again. So, this claim again holds now, namely that every vertex enters, and every vertex, I should be correct here, every vertex reachable from S from S enters and exits Q exactly once. So, I can still use that notation, okay. We can use the total order to indicate which vertex exited the queue first. This total order is only over all the vertices which are reachable from the vertex S. Those which are not reachable will never figure in this whole process. Another trivial claim is that S0 is contained in S1 is contained in S2. This is empty set. This contains only vertex S, and then subsequently one vertex is added into this each time in each iteration. Another straightforward claim similar to the earlier case is that dV denotes the weight of a path from S to V at any time. The value of dV has been set as the value, the d value of its parent, say parent is u, then it is always equal to du plus weight of uv. So, you can always trace it back, you go back, this is wuv, then trace back to its parent and just keep going, you reach S. This is the only vertex which does not have a parent. So, this path will end up in S, and the d value is precisely the sum of these weights. Hence, it is a path, not necessarily the best path, but it is a path whose weight is dV. So, that holds. Now, I would like to make a slightly non-trivial claim, claim 4. So, to describe this, let me just go back to the picture. We have Si here. This is the picture after ith iteration. For any vertex x inside Si and any vertex outside Si, we claim that the d value of x is always less than equal to the d value of y. So, for all after any iteration I, for all x in Si and y in V minus Si, outside Si. The d of x is less than or equal to d of y. Notice that earlier a stronger claim was made in this regard. What we said was that the q was a normal q and the value, the d values of the things ahead were less than or equal to d values that was left behind. Now, the structure is not that simple, it is a priority queue. We cannot say much because by definition what is ahead is one which has got less d value, which is inherently true. But what we are claiming is that once something goes out of the queue, if it goes out of, it goes inside set S, then every subsequent d value will be greater than or equal to that value. So, how do we prove this? We will try to show this by induction on iterations. So, by induction on iterations. Well, in the first iteration, there is only S inside, or let us start with the second iteration. So, there is only S. So, at the end of the first iteration, okay, base case is that S1 is only S. Its d value is 0 and the d value of everything else is going to be non-negative. So, clearly such a claim is true because there is only one guy in S1. So, x is S, everything else will be automatically 0 or more. So, this is trivially true. So, now let us try to prove the induction step. So, our induction hypothesis is that the claim holds after I minus 1 iterations. So, let us take a picture. This is S I minus 1. Let us say the vertex that we select at the start of ith iteration is u. So, after one iteration this will be our Si. Pick any x, any y here, then from this claim dx, remember the d values of these never change. So, I am going to denote dx as the final value of x, d value of x. This is less than equal to the di minus values of all these, but by definition this is the smallest di minus 1 value. This is how it is selected. So, this is less than equal to di minus 1 u, which has to be less than equal to d I minus 1 y for all x in S I minus 1 and y in V minus S I minus 1 minus u, everything outside, S I minus 1 and u. Okay. This inequality is because of the choice of u, and this inequality is due to the induction hypothesis. Now that we have this, note that the d value of u, because u has been selected in the algorithm, never changes. Okay. So, d I minus 1 u is also the d value of u, which for clarity I would say final. So, this picture now turns into S I, okay, these are the values including u and all y's here. So, what we have here is that d of x is less than equal to d of I minus 1 y. Now, S includes u as well. Okay, so far so good, but to prove our claim we need to show that this is also less than equal to the I of y. So, let us pick any y here and look at what happens in this ith iteration. Well, there are two possibilities: either the d value of y does not change in our algorithm, we set its value in case it is a neighbor of u to the minimum of the old d value of y and the value du plus w uy. In both cases, notice that the dy remains greater than equal to du, it never decreases. In case y is not a neighbor of u, then we anyway do not change. So, what we notice is that this value, namely d I of y, is still greater than equal to the d value I minus 1 of u, which is same as d of u, the final value. Okay. Once again, let me just quickly run through this point, that all y that are outside Si can be split into two sets, those which are not neighbors of u. Their d value d I minus 1 is same as their di, and they were always greater than equal to this value. So, no change there, this inequality holds. In case if y is a neighbor of u, then there are two possibilities. We compare the d I minus 1 of y with d of u or I minus 1 of u, which is same, plus weight uy. If this is greater than this, we do nothing, but then this is greater than equal to this value. Otherwise, we set it equal to this, still it is greater than equal to this value. So, in all situations, the new value of y remains greater than equal to this. And this value was greater than equal to the d value of everybody else here. That was the story here. So, still what happens is that, so the d value of every x is less than equal to d value of ith value of y for all x in Si and for all y in V minus Si. Okay. Now, one direct consequence of this, what this means is that every time a vertex comes in, its d value has to be greater than equal to the d value of everything present in this. So, a corollary is that if U enters S before V. Remember, if U exits Q, it enters S. So, if U exits the Q before V or U enters S before V enters, then the D value of U, the final value of this has to be less than equal to D value of V. When I do not put a superscript, I mean this is the final value in this case, or maybe I should put that. So, this is essentially a similar kind of result that we had in the previous case. Okay. So, the last claim now, the claim that we want to make is that the final D value, what we want to show is that D final of every vertex is its shortest path value, the weight of the shortest path from S to U. We want to prove this. This is our final objective, but we will not be able to directly prove it. We will prove this along with another claim and we will try to prove both simultaneously. So, let me state the claim, which has two parts, that d I of V is del W S I S to V for all V in current state, and 2, the D final of V is del W of S V, which is also del W S I of S V for all V in visit complete state. There is something hidden in this claim. Let me just look at this. What we are saying is this claim that the final value is same as the shortest weight from S to V, but it is also this, which means this says that there is a path of the shortest weight from S to V. V is already in visit complete, all intermediate vertices for such thing must be in, which means the entire path is contained in Si. Okay. There is a shortest path and it is also, there is at least one such shortest path is inside Si. Okay. This is the full meaning of this claim. Here we are saying something that the current D value, that is after ith iteration, it is the best among the PSI paths. Remember, the PSI paths were those paths which had all but the last vertices inside Si. So, we will try to prove these two claims simultaneously. Okay. Now, the claim again by induction is valid in the base case. What is happening in the base case? I am again taking my base case as case is when I is 1 after the first iteration. In that case, you have your S1 containing only S, only vertex in visit complete state is, this is at the end of first iteration. So, the only vertex qualifies to be in S1 is S. So, the vertex for which we have to check this is S. D final of S is 0, this is 0, this is 0. This is 0 because the path is empty path which starts here and does not go anywhere, just stays there. As far as these are concerned, these are the current vertices are those which are directly incident on S, the neighbors of S, and their d values is nothing but the corresponding weights. So there cannot be a second path. These are the only possible paths to x1, x2, etc., which are in current state. So the delta WS1 will be the weight of these edges, because these are the only paths for corresponding vertices. If there is only one path, so this is the delta value, and that is exactly what we have set. The d values of these are set to be precisely d of S, which is 0 plus this weight. So it is trivially true, okay, is okay. Remember that S1 is S, okay. So there is nothing complicated about this claim for the base case. So let us now come to the induction step. Let me assume that in the ith, suppose in the ith step U is selected. So my claim holds for first I minus 1 iterations, and the ith iteration just begins. This is Si minus 1, here is U, we have just selected, there is S inside this. Select any one shortest paths that go from S to U. So it might go like this, any number of times it might exit the set, it might enter the set. I am just picking some picture here. So the weight of this path is what? Delta WSU. This is in absolute sense one of the shortest paths without any restrictions. So consider the path and start from S and look at the first vertex that goes out of Si minus 1. Remember, there is U which is outside this. Okay, this is the picture with respect to I minus 1. So certainly there is one vertex which is outside, so this path has to go outside Si minus 1. Say the first vertex it hits is X. Let me first assume that X is different from U. Then a few inequalities I can now write down. Okay. So the delta W of Sx is equal to delta W Si of Sx. The reason is, if this is the shortest path from S to U, then this has to be the shortest path from S to X. So the weight of this path is absolute minimum weight. But this happens to be one of the PSI paths, because all vertices except S are inside Si minus I minus 1, I should say, Si minus 1. So this qualifies for also this, they are equal. From induction hypothesis, this is also di minus 1 x. Notice that induction hypothesis applies for I minus 1. So, this is equal to this, all right. Now, let us look at u. Note that the path goes further up to u. So, the delta w of S u must be less than or equal to this value, because it goes further. Maybe the weights are 0 here, so they could be equal, but that is about all. Then let me just draw it somewhere here. By definition, this has to be S minus 1 of S u, because this is the best path with respect to a restriction. This is the best path, absolute sense, and this has to be d I minus 1 u. Okay, this comes from induction hypothesis. Now, notice that there was a certain condition subject to which u was selected. The u was that vertex outside S I minus 1 which had the least d value. So, from the choice of u, d I minus 1 u has to be less than or equal to d I minus 1 x. So, what happens is that this is equal to this, forcing these inequalities to turn into equalities. Okay. So, that this thing is now equal, this thing is equal, all of them are equal, all right, they must be equal. Now that we have the equality of all these entities, what we notice is that del w S x is d I minus 1 u, and this is also del w S I S u. What this means is S I minus 1, my mistake, I minus 1. So, what we have is that in S I minus 1, there is a path which is completely inside except in the last vertex. This is, and this is also the absolutely shortest path, one of the absolutely shortest paths. Okay. This has weight w S u, which is also the S I minus 1 S u. But this is the final value of u. Okay. This is also d final of u. So, what we have concluded is that the next entrant into set S has its d value, the final value, equal to its optimum distance, or the distance actually, the minimum shortest path. So, let us come back to this and look at the this claim, the second claim. What we wanted to say is that for all vertices with visit complete state, which means those are which are in S, their optimum value is their d value. What we did is we proved that this is also true for the new vertex that entered into set S. So, induction says therefore, this holds, but this is not complete unless we also prove this claim. So, now we will try to show that everything else will have, everything outside, everything in current state will have this thing true. So, let us now prove that claim. Well, what happens now is that this is your SI with u included in it, and pick any vertex y out there. Okay. What we know is that d of di minus 1 y is del w s I minus 1 s comma y. This is from the induction hypothesis. This is what happened after I minus 1 iterations. Let me just put y here, and I want to show the same thing at the end of the ith iteration. Well, what happens when y is a vertex which is not adjacent to u? If it is not, then the path, well, let us just assume, irrespective whether it is adjacent or not, let us consider a path now. Let me directly do that. Let us suppose we have a path like this. Okay, these are the only new paths that we need to worry about. Those paths which do not contain u are already in this, they are accounted for. So, the only possibility is that there is a PSI path which contains u and it is better. Okay. But I am assuming that u is not the pan ultimate vertex, the second last vertex on this path. Say it is something before that. Let us say this is x. Well, then we know from first claim that the shortest path from S to x, x was present in Si minus 1, x belongs to Si minus 1 because the last vertex was u. So, there is a shortest path from S to x contained in Si minus 1. So, I can take that path. So, let me pick that path. Let us say that path, this is that path. This is something which does not use u. So, the weight of this path being optimum will be same as that weight or less than or equal to this weight. So, this pink path followed by this edge must be the, must have the same weight as this or less. So, I have an alternative path from S to y which does not even use u. So, I do not need to even consider such a path, its weight is not going to be better. So, I need to only worry about those paths which contain u and u is the second last vertex. So, let me just consider that. Here is this Si, this is S, this is Y. If Y is not incident on U, okay, if Y is not in the neighborhood of U, this denotes all the neighbors of U, then there is no such path. Then di of y is same as di minus 1 of y, which is same as del what? Del w s I minus 1 of s comma y. Okay. But since no better path is found including u, then this is also why not in, oh sorry, why not in, my mistake, why when it is not a neighbor, This was the case when it was not a neighbor. There was no change. Thank you. So, in that case, the claim that d I y is del w s I s y. Second case is when, next is when y is in n u. So, there is an edge from this. So, there are two types of paths, either they do not use u, PSI paths, or there is a path which goes like this and goes through this. These are the two paths. Well, the weight of this path is clearly del SU plus weight of uy, and this thing is equal to d of u. So, it is a du plus w uy, and the weight of this path, the best path, is same as d, I would say delta I minus 1 s u, and which is same as d I minus 1 u. So, the best path of this kind has this weight, best path of this kind has du plus w u y. And in our algorithm, all we do is compare these two values and pick the best. So, whichever is smaller, that will be the new value of dy. So, in that case also we notice that diy is now the delta w s I s y. Okay. This is the best path of this kind. So, we have established the first claim as well. Now that we have proven the both statements hold for ith iteration, the induction argument is complete. Yeah. So, what we showed is that for every visit complete vertex, the d value is its optimum value, that is d final for every vertex. This is a corollary. The d final value of every vertex is its best value in the graph, okay. Because finally, when the algorithm is over, every vertex ends up in S. So, and that value is the d final value. So, this is always true. And finally, the graph that we output, the graph we output is parent of x, x, all these tuples, x in V minus S. Is indeed the shortest weighted shortest path tree. The reason is that for any vertex x, if we trace it back, parent of x and so on, we reach S. These edges are part of this graph. Okay, this is the set of edges. The set of vertices are all the, I should point out that those which are reachable only will figure in this, otherwise they are isolated. So, this path is a path in T, and the weight of this path is precisely dx, and that is same as delta w sx, okay, which is same as now we can say that this is the optimum, this is the optimum distance in the graph, and this is also the optimum distance in T in this subgraph. And for every vertex we will basically will find, maybe it ends here some, and then it goes up some vertex and so on. So, what happens is that this tree, this will be a tree, because there are only n minus 1 vertices, edges, if everything is connected. So, if you ignore those unreachable vertices, say there are n reachable vertices, there are n minus 1 such edges. Each has at least one edge incident on it. So, it is a, there is no isolated among them. So, this is a tree, and the path lengths in the tree are equal to their optimum distances in the graph. That is our definition of the weighted shortest path tree for S. So, this is the end of the lecture. Thank you.